Assalamualaikum, students and fellow physics enthusiasts. In today's episode, we analyze a transverse wave produced in a rope. How do we calculate the speed of this wave and its wavelength? We will find it out, so just hang on, watch, and learn. The question is, you are testing a mountain climbing rope that has a linear mass density of 0.0650 kg per meter. The rope is held horizontal and is under a tension of 8.00 times 10 to the second power Newton to simulate the stress of supporting a mountain climber's weight. Question letter A. What is the speed of transverse waves on this rope? Question letter B. You oscillate one end of the rope up and down in simple harmonic motion with frequency 25.0 Hz and amplitude 5.0 millimeters. What is the wavelength of the resulting waves on the rope? Question letter C. At time equals 0, the end you are oscillating is at its maximum positive displacement and is instantaneously at rest. Write an equation for the displacement as a function of time at a point 2.50 meters from that end. Assume that no wave bounces back from the other end. We are given the linear mass density of the rope. Mu equals 0.0650 kilogram per meter. And the tension force F on the rope is equal to 8.00 times 10 to the second power Newton. And we are also given the frequency small letter f of the transverse wave, 25.0 Hertz. And the amplitude of the wave, capital A, equals 5.00 millimeters. Our target variables are letter A, the speed of the wave, for letter B, the wavelength lambda, and for letter C, okay, we are to find an equation for the displacement y as a function of time at a point x equals positive 2.50 meters, all right, from the end of the rope where x is equal to 0 at time equals 0. Solving for the speed of the wave v, we use the formula wave speed v equals square root of the force F, or the tension force F, over the linear mass density denoted by mu. All right. So substituting the given, we have square root of 8.00 times 10 to the second power Newton divided by mu, which is 0.0650 kilogram per meter. Doing our math, we find that the wave speed v equals 111 meters per second. Now for the wavelength lambda, we just divide the speed v by the frequency small letter f. That is 111 meters per second divided by 25.0 hertz. And we get for the wavelength lambda equal to 4.44 meters. Graph 1 shows the wave function y quantity x and t as a function of x for a specific time t equals 0. It gives the displacement y of a particle from its equilibrium position as a function of the coordinate x of the particle. So at time t equals 0, the wave function may be expressed as y quantity x, okay, at time equals 0. One form of the wave function is a, which is the amplitude, multiplied by cosine 2 pi x over lambda, where lambda, of course, is the wavelength. And in this graph, we also emphasize that the vertical positions of the particles at time t equals 0. For instance, particle A is at the maximum displacement or y displacement. All right? It is at the maximum positive y displacement. In other words, it is located at the amplitude of the wave, which is 5.00 millimeter. All right? Now, this particle A is instantaneously at rest, and after time equals 0, it is about to move downward back to the equilibrium position. All right? But right now, what we are looking at is the position of these particles at time equals 0. So at time equals 0, we say that another particle B is at its equilibrium position. And at that instant, particle B is said to be moving with a positive velocity. That means it is directed upward. Okay. Uh, the velocity of any particle is said to be at maximum when it is located at the equilibrium position. All right. Now, the other particle at the same instant, time equals 0, particle C is at its negative or maximum negative displacement and momentarily at rest as well. Particle D is also at the equilibrium position, but it is actually moving in the downward direction, so its instantaneous velocity is negative v sub y. And last but not the least, we have particle E, which is also at the maximum positive displacement and momentarily at rest. All right? So these particles A, B, C, D, and E are just arbitrarily chosen to represent the different particles in the medium, which is the rope. All right? Notice that the distance between particle A and particle E defines a wavelength lambda. All right? In this graph, we indicate the lambda as the distance, horizontal distance, between the two consecutive or successive crests. but that could also be the horizontal distance between two successive crests. All right, this is the trough, and these are the crests of the wave. All right, the type of wave that we are talking about, okay, is a transverse wave. It is because these particles in the medium, all right, such as particles A, B, C, D, and E, are in fact vibrating up and down, all right, relative to the horizontal or with respect to the what we call equilibrium position, all right, as indicated by the arrow that represents the instantaneous velocities, all right. So since the vibration is perpendicular to the wave motion, all right, we say that this type of wave is transverse. Okay, we emphasize that the wave propagation is to the right or from left to right, while the vibration of the particles is described to be up, down, perpendicular to the horizontal wave motion. Here's another graph, but this graph, number 2, shows the wave function versus time t for a specific coordinate x. It gives the displacement y of the particle at x as a function of time. That is, it describes the motion of that particle. Okay? So at position x equals 0, we say that the wave function y quantity x equals 0, all right, at any given time t, okay, can be expressed as the amplitude of the wave, capital A, multiplied by cosine 2 pi times the time t, small t, divided by the period of the wave, capital T. All right? So, graph 2 may look exactly similar to graph 1, but they are two different graphs. While graph 1 is uh, the displacement as a function of the horizontal coordinate x. Graph 2 is the wave function, okay, as a function of time. Notice that we indicate here, all right, the time it takes for one complete cycle or vibration, all right. For instance, at this point to that point, that is equivalent to the period labeled as capital T. Lastly, at a point x coordinate equal to 2.50 meter, we find the equation, all right, uh, for the displacement as a function of time t, right? And the wave function y quantity xt can be expressed as the amplitude capital A times cosine 2 pi multiplied by x over lambda minus time small t divided by the period capital T. So this is just one of the several ways of expressing the wave function, all right, for the displacement y as a function of time t, right? So based on our given or required value for x, which is positive 2.50 meters, we substitute for the amplitude of the wave expressed in millimeter. We have 5.00 millimeter, okay, to be multiplied by the cosine 2 pi quantity 2.50 meters. This is the specific x coordinate, all right, positive 2.50 meters, and that will be divided by the wavelength that we earlier calculated, 4.44 meters, all right. So the result of dividing this value for x and the lambda will be or the ratio of the time t to the period, that is 0.0400 seconds, will still have to be deducted from, all right, the quotient of dividing x over lambda before we multiply the result to cosine 2 pi, and of course to the given amplitude 5.00 millimeter, all right. So at any given time we can determine what the displacement of a particular x, in this case positive 2.50 meters, all right. So at any given time, for example, at time equals 0, all right, we earlier mentioned that in our uh, illustration earlier, graph B, all right. But likewise, you can determine the y displacement of that particle x equals 2.50 meters, okay. For example, at any given time, such as 1 second, all you have to do is substitute that value of the time t in this equation, all right? And then just do the operation to determine the vertical y displacement. But for now, since we are only asked to write the equation of the wave function as a function of time, so we just simplify this and come up with this answer, all right? So the wave function y as a function of time t is just expressed as 5.00 millimeter multiplied by the cosine of the difference between 3.54 radians and 157 radian per second, which will be multiplied by the time t, all right. This is the equation of the wave function for the x equals positive 2.50 meters, all right. In other words, for a particle that is 2.50 meters away from the first particle, all right, x equals 0. So that's it. We are done with our tutorial for this topic. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.